What's up, guys? Welcome back to The Trident. Happy New Year to everyone. I'm your host, Millie, and today we have something special for you. As the new year symbolizes a new beginning, keeping that in mind, today we will be talking about the beginning of life itself. What is the earliest evidence of life on Earth? Where did it come from? Who discovered it? And what can it tell us about the incredible journey of evolution? Our planet formed about 4.5 billion years ago, but life didn't begin right away. For hundreds of millions of years, Earth wasn't exactly a friendly neighborhood. It was a chaotic, inhospitable place bombarded by asteroids, covered in molten rock, and surrounded by a toxic atmosphere. Yet, around 3.5 to 4 billion years ago, during the Archean Eon, something extraordinary happened. The first signs of life appeared. The earliest life forms were microscopic, single-celled organisms that thrived in the oceans of a young Earth. But how do we know this? What evidence proves that life existed so long ago? Let's find out. One of the most compelling pieces of evidence comes from stromatolites. These are layered, rock-like structures formed by ancient microbial communities, particularly cyanobacteria, also known as blue-green algae. The oldest stromatolites date back to about 3.5 billion years ago and were discovered in the Pilbara region of Western Australia. Paleontologist J. William Scoff and his team, who discovered these stromatolites, revealed that the stromatolites were created by colonies of microorganisms living in shallow marine environments. Now, what is the importance of these stromatolites? Well, they provide the earliest direct evidence of life on Earth and show that these microbes were already performing photosynthesis, a process that would later oxygenate the atmosphere of our planet. Not all evidence of early life is visible to the naked eye. Some of it lies in chemical signatures, specifically isotopic ratios of carbon. In Greenland's Isua Greenstone Belt, researchers found rocks that are 3.7 billion years ago containing traces of carbon-12, a lighter isotope that living organisms utilize. These isotopic signatures suggest the presence of life even though no fossils remain. In the 1980s, microfossils were discovered in a rock formation called the Apex Shirt, also located in Australia and dated to be about 3.5 billion years old. These microfossils are microscopic impressions of single-celled organisms, most possibly bacteria. These tiny fossils give us a concept of what the earliest life might have looked like: simple, prokaryotic cells living in warm, nutrient-rich waters. Beyond fossils and chemical signatures, we also have evidence of life's building blocks, the organic molecules, such as methane, nucleic acids, proteins, carbohydrates, etc. In 2008, scientists examined 3.8 billion years old rocks from Greenland and found traces of organic carbon, a fundamental component of life. These molecules weren't fossils, but chemical remnants of ancient life forms. Another thing that is even more exciting, researchers have found amino acids, the building blocks of proteins, in meteorites. This suggests that the ingredients for life might have been delivered to Earth from space, kick-starting the process of abiogenesis, the origin of life from non-living matter. Another interesting clue comes from hydrothermal vents, underwater geysers that spew out hot, mineral-rich water. Modern studies have shown that these vents host entire ecosystems based on chemosynthesis, a process where organisms derive energy from chemicals rather than sunlight. Scientists believe similar environments may have existed on early Earth and could have been the cradle of life. Recent discoveries of fossilized microbial mats around ancient hydrothermal vent systems support this theory, pushing the origins of life further into Earth's deep oceans. These early life forms weren't just sitting around, they were evolving. Through mutations and natural selection, these simple microbes diversified. Some developed the ability to photosynthesize, which gradually increased oxygen levels in the atmosphere during the Great Oxidation event around 2.5 billion years ago. This oxygen boom paved the way for more complex multicellular life to evolve. Fast forward a few billion years and we see the rise of eukaryotic cells and eventually the first animals during the Cambrian explosion about 540 million years ago. But why should we care about these ancient microbes? What do they teach us? First of all, early life forms are the foundation of the evolutionary tree. Studying them helps us understand how life diversified into the millions of species we see today. If life was possible under such harsh conditions on Earth, could it happen elsewhere? The search of ancient microbial life on Mars and other planets is directly inspired by these discoveries. Fossils and biomolecules provide vital clues about how life began, a question that has fascinated scientists for centuries. The earliest evidence of life on Earth, from stromatolites to isotopic signatures and chemical evidence, these things can give us a potential view into a world billions of years old. It shows us that life is stubborn and versatile, capable of emerging in the most extreme environments. As we uncover more fossils and chemical traces, we get closer to answering profound questions. How exactly did life begin, and could it exist elsewhere in the universe? Thanks for joining us on this incredible journey through time. If you enjoyed this video, don't forget to like, subscribe, and share your thoughts in the comments. Have a wonderful new year and stay tuned. We will see you soon in our next presentation.